Today we'll be creating this Mandelbrot displacement effect in Blender 3.4 using geometry nodes and Eevee. We'll start by walking through how to create the Mandelbrot fractal in geometry nodes, and then move on to setting up the material, the animation, the lighting, and the rendering. The project files are available for free on Gumroad, so if you want to follow along with those, get them from the link in the description below. So let's get started with a brief explanation of how to calculate the Mandelbrot set. Calculating the Mandelbrot set is based on the equation z equals z squared plus c, where z and c are complex numbers. Since complex numbers have two parts, where one part is imaginary and the other is real, you can think of complex numbers as points on a two-dimensional plane, where the real part corresponds to the x-axis and the imaginary part corresponds to the y-axis. One way to draw the Mandelbrot set is to start with a point representing z located at 0, 0, and then update its position with the equation z equals z squared plus c until the length of the vector representing z is greater than 2. Here we see the point starting at 0, and now one iteration of z equals z squared plus c, where z will be equal to c, and now a second iteration, a third, and now many. As you change the value of c, which here is represented by the blue dot, you can see that when c is within the Mandelbrot set, the points produced through each iteration of z equals z squared plus c never escape the red circle. But if you move c outside of the Mandelbrot set, the values of z end up outside of the circle. You can use the number of iterations it takes for z to escape the circle to generate the coloring pattern seen in most Mandelbrot visualizations. Simply mapping the number of iterations to a color will produce a stepped pattern as seen here. But there is another technique which can be used to create smooth shading, which will produce the final image. So let's go over how to do all of that in geometry nodes. So to start out, we initialize the grid. And the grid is really just a 2D image. So looking from the top down, we've got a very detailed grid. I have it set to be 2048 by 2048 points. Let's put that down to something a little bit more sane to start out with. So this is 256 by 256. It's not going to be quite as detailed, but it will run a lot quicker. And all we're doing here is we're creating a grid mesh with 256 vertices in the x direction by 256 vertices in the y direction. Size is just 1, 1. We're storing the iteration count in a floating point attribute for each point. And we are also storing a z attribute, which is going to be the complex number representing z in our Mandelbrot calculations. And we're storing these as attributes because as we go through the iteration node groups, we'll be updating those values within attributes to keep track of them for the entirety of the calculation. So if we dive into the iterations node group, we have a series of chained iteration group node groups, which themselves are groups of chained iteration node group. So this is just doing a bunch of iterations on z equals z squared plus c, which is within this iteration node group. And diving into the iteration node group, we see the z equals z squared plus c node group is here. And then we do the escape condition. So this is testing whether or not the length of the z vector, or the complex number z, is greater than a value. Now, in the example that I talked about at the beginning, I said it would be greater than 2. And that is technically true for calculating whether or not a value of c is within the Mandelbrot set or not. But for the smooth shading, we're going to use a larger value. So if I put this down to 2, you'll see that you get kind of these odd coloring effects over here. And that's because when you're doing the smooth shading, you need a larger value of the length of z for the escape condition for mathematical reasons that I do not fully understand. So if the escape condition is met, then we don't change z or the iteration count, because this value of z is outside of the circle. Its escape condition is true, so we don't want to update the iteration count at all. If it's not true, then we update z by z equals z squared plus c. We increment the iteration count by 1, and then we store those attributes back into the geometry. So we're just updating the iteration count and the value of z by either z squared plus c for z if the escape condition is not met, and we add 1 to the iteration count again if the escape condition is not met, and if it is, then we don't change those values at all. So diving into the z squared plus c node group, we see two major sections, one for z squared and one for c. Let's look at c first, because c is really just a point in space. So when you're calculating the grid for the Mandelbrot set, you can see how you're not seeing the entire Mandelbrot set in this view right here. You're actually just seeing a zoomed in version of it. And this entire node group is just set to find a place that's interesting within the Mandelbrot set that I want to zoom into. So there's translations and there's scaling. So if I move this scale parameter, I'll zoom in and out. And if I move these values, I will translate in the directions that I'm changing. And so I've got one translation scaled to a very low value. It just says 000 here, but it's actually 0.0001. And then a slightly higher value, and that's so that when I'm scaled at different distances, I can move quicker using this to find a spot. But when I'm zoomed in a lot closer, if I move these values, I'm just going to move really quickly. So I want a bit more fine-grained control. But really, you don't need any of this, and this could really just be position. But you might not be zoomed into the area of the set that you want to be. So if you have specific values of c that you want to use, you can. It's really an offset from the position. So you're using every point in the grid as a value of c to then pipe through many iterations of z equals z squared plus c, where z starts at 0, and you're recording the number of iterations that it takes for z to have a length that's greater than a certain boundary condition, and then you use that value to determine the coloring that you see here. So continuing on with the z equals z squared plus c equation, we'll move up to this z squared frame. And this is z squared, and z is a complex number, so it's not exactly the same as taking the square of two real numbers. And the way that you square a complex number is you take x to the power of 2 minus y to the power of 2 as the x component of the new complex number that is the result of the squaring operation. And then as the y component of that output number, you take the x and y of the input multiplied together, multiplied by 2. And so that is how you calculate z squared. Then you use a vector addition node to add c to z squared. And that is the z squared plus c node. And so to recap quickly, you take in the z attribute, you pipe it into the z squared plus c node group, you get the output of that operation, and if the boundary condition is not met, you use that value to store into the z attribute. If not, you keep z the same. A similar thing is true for the iteration count. If the boundary condition or the escape condition is not met, you add 1 to the iteration count. If it is met, you keep the iteration count the same. You store those attributes, and then you repeat that step many times in order to calculate whether or not the given point in the grid is part of the Mandelbrot set or not. And if it is not part of the Mandelbrot set, how many iterations it takes to escape the boundary condition. So next, let's take a look at the coloring. I've got this smooth coloring frame up here. And as I mentioned before, if you just use the iteration count that it takes for the z equals z squared plus c equation for any given point in the grid to escape the boundary condition, and you just use that iteration count for the color, you'll get this stepped pattern. And we want a smooth pattern, and that is done by adding the fractional part of the iteration count to the iteration count. So to go over the fractional part node group, first I'll caveat by saying I'm not going to go into the math of why this works, nor do I fully understand it, but I will link to a Wikipedia article called Plotting Algorithms for the Mandelbrot Set that I pulled this smooth algorithm from. It's in the section called Continuous Smooth Coloring, so you can check that out in the description if you want. And so here I'm just going to go through the inputs, the transformations, and the outputs. So the input here is z. You're going to separate the vector so you can isolate the x and y components. And then I have this log zn node group. And what that does is it takes the square of x and y, it adds them together, it gets the logarithm of that operation, and then it divides the output of that logarithm node by 2. Then this new node group takes in the output of the log zn node group, and then it takes a division of log zn by log 2, or logarithm of 2, takes the logarithm of the output of that division operation, and then it divides this logarithm by log 2. And that gives you almost the entire fractional part. You actually have to subtract the output of the new node group from 1, and that gives you the value that you need to add to the iteration count to achieve these smooth rather than stepped results. And now we can move on to the shader preparation frame. And really all we're doing here is we're taking the output of our smooth coloring operations and we are mapping that into a range between 0.1 and 1, and then taking the power of that mapping to an exponent of 0.1. And this is all just for artistic purposes. So let's get into that. The core to this mapping is the attribute statistic node. So we're taking the minimum and maximum values of the smooth coloring value for each point in the geometry, and we are squishing those ranges of values between 0.1 and 1. And that's just to get a better handle on the values that we're dealing with, because they could be all over the place otherwise. Then we are piping the output of the map range node into a power node, with an exponent of 1. You can play with this exponent if you want. It's purely an artistic decision. If I have it at 1, it's going to be much taller with much more changes to the color. 0.1 will also smooth out the changes. I could go even smaller, get flatter. Really depends on the look that you're going for. So let's go with 0.1 here. And then the output of this power node goes straight into a stored floating point attribute on points called the fractal gradient, which we'll use in the shader nodes to create the coloring that you see here. And lastly, there is this displacement frame, which simply does further transformation with a multiplication node on the output of this power node, and then uses that value as the z component of a vector that offsets the positions of the grid geometry to create the displacement effect. Without that, you'd get the coloring changes, but you wouldn't get any of the displacement. So let's rehook that up. The last node in this network is the set to shade smooth, which we do because it looks nice. And now we can move on to the shader nodes. Before we do that, I'm gonna go ahead and set the grid resolution from 256 to 2048. It'll take a bit of time to calculate initially, but once it's done, you'll be able to move around the scene quickly. We can also play the animation that we're about to set up in the shader nodes, and it will run interactively in Eevee. Moving right on to the shader nodes, if we go into the shader editor, we can see this network where first we bring in the fractal gradient attribute with an attribute node here. We take that factor because it's just a floating point or scalar value, and then we do some artistic manipulations on that along with an animation driven by this expression in this subtract node, which creates the animated coloring that you see in the viewport now. It then pipes that artistically created coloring into a principled BSDF, which has very high specular value, very low roughness value. Overall, pretty simple shader. So let's go through the nodes that we use for coloring. First, we multiply by 12. If you change that value, you'll get more changes to the colors. If you make it smaller, everything will be a lot more uniform and change much slower. I picked 12 in this case. And then you subtract a certain value. If I just use a different subtract node without a driver on it, you can see that if I just change that value, it will move the colors either up or down depending on the direction that I move the subtraction in. And we can look at the expression for the driver by clicking on the value field, and you'll see that the driving expression is the frame of the animation times 0.01. The way you create a driver like that in an expression, or create an expression driver like that in a value field, is you click on that field, you enter a hashtag, and then you can use the expression that I have above, and so that uses an inbuilt expression variable that's frame, and then multiply that by whatever you'd like, 0.01 in this case, 0.01, and you'll get the same value as up here. Then you pipe the output of that subtraction node into a wrap node, and that's so you get this continuous cycling of colors. If I didn't use the wrap node, you'd very quickly get to nothing, and I don't know exactly at what point you even see the correct colors. Everything is green because we're all the way to this end of this color ramp spectrum. So the wrap node is very important. Minimum of 0, maximum of 1. So if this value is above 1, it will wrap back down to 0. If it's below 0, it'll wrap back around to 1, creating this infinite cycling. And then the color ramp node is where a lot of the magic happens. I have it set to an HSV color mode so that the interpolation between these colors kind of wraps around the hue wheel. I have it set to clockwise. You could set counterclockwise, not nearly as interesting. You can do near and far as well. In this case, far is similar to clockwise, but clockwise is a good way to do it. If you set to RGB, it'll just interpolate across the color spectrum rather than around it. So these are good settings there. You can create a whole bunch of color ramps as you see fit. If I delete that black node, you can get this rainbow coloring. Maybe you want less of a range of colors. You can set that back to RGB and get something like this. If you'd like to wrap back around to that green, you can make sure the beginning and the end of the spectrum are the same, and you could just start adding in colors as you wanted to. So there's a lot to play around with there. This is what I came up with. So again, this principled BSDF node has a very high specular value. I think that looks really good for this effect. Roughness is low. Higher roughness will give you something that looks different. I like this low roughness. In fact, even lower might even be good. But let's stick to 0.15 for now. So moving on to some of the rendering settings. We're using Eevee as the rendering engine. We've got ambient occlusion turned on. You can see the difference there. Also screen space reflections, quite nice. Add a little bit of illumination that I enjoy. I have half res trace turned off, high trace precision. You can play around with these values as you see fit. I've got color management set to filmic, just the default settings here. The other important factor for the rendering is the light. I've got a single directional light set to a fairly wide angle of 32. Strength is at 2. And then in the shadows, it's important to have contact shadows turned on. Without them, you don't get nearly as much of the detailed shadows as you'd like, so make sure to turn those on. Here are the settings that I have for those. And if we switch to the camera view mode using 0 on the numpad, we can see that the last part of the animation is the camera movement. This is done with a fairly simple setup where you have a camera and a camera parent. So this camera is the child of the camera parent, and the camera parent simply has a driver on the Z rotation property. So this rotates slightly along the Z axis every frame. And so again, to add a driver to a property like this, you'll do a hashtag. And then in this case, I have frame divided by 2048. and then something else, I multiply by pi times 2. And so that will cycle every 2048 frames. So if you wanted to make this into a looping animation, you can make sure that this value is set to however many frames you have in the entire animation, so that the camera will seamlessly loop around its position from the end frame to the beginning frame. In this case, we have it set to 2048, but we aren't rendering the entire looping animation. We're just going to frame 512. And then the angle of the camera is based off of its own position. So if you want to change where the camera is relative to its parent, what you can do is press N to open up this menu and lock the camera to the view, and then just use your normal viewport navigation controls to move the camera. And then when you press play, it will still be a child of the camera parent and therefore rotate accordingly. And that is it. So to do a quick recap, we have this Mandelbrot object with a single geometry nodes modifier on it, which has our Mandelbrot displace geometry nodes network, which we covered in this tutorial. It is also connected to a material defined by this shader node network. It is connected by object. That's important. If you don't see the material showing up on the object, then one thing that you can do is you can actually set it within the geometry nodes node group. The way you'd do that is you'd add a set material node in. It's going to take a bit of time to calculate because it needs to recalculate all 2048 by 2048 points. I'll go ahead and put that to a lower value for now, just to show you. Then you'd add that set material node in there, set that to Fractal, and that'll do the same thing, because sometimes if you have it linked to the wrong setting, it won't show up if you have the material won't show up on the object if you have geometry nodes applied to it. So you've got that single object with the geometry nodes modifier on it. You have a single directional light. You can rotate this, move it around to achieve different lighting effects as you please. I'm going to set this back to 2048. Then you have the camera, which gets animated by its camera parent, which uses a driver to rotate around the z-axis. You can also play with, the focal length of the camera. One thing that I may have not covered is the depth of field. That is on the camera object here. I have the focus object set to be the camera parent. You can turn that off and just do it by distance as well. And then you set the f-stop. Lower will create more blur outside of the focus range. Higher will create less blurring. So really, to have fun with this project, what you want to do is you want to create this setup to create the Mandelbrot fractal, and then you want to find a fun area to focus on. And you can do that within the z squared plus c node group using transformations in this C frame. So you can set those accordingly and move around. If I try to set it now, because it's 2048 by 2048, it's going to take a long time to process. So make sure to set the resolution to a much lower value where you're trying to find an area of the fractal that you want to render. And then once you've found that, you can play around with the coloring and the shader nodes, play around with your animation, all your rendering settings, and then create cool fractal animations as you please. So as always, I hope you enjoyed this tutorial. I hope you learned something. I hope you had fun. And I hope you have a ton of fun playing around with creating cool Mandelbrot fractal animations. Until next time, goodbye.